Hi, my name is Jessica Smith, and I'm a research associate at Harvard University and one of the science leads of the DCOTS mission. And the objective of the mission, of course, is to understand the impact of very strong thunderstorms on the composition and the chemistry of the stratosphere. And this, of course, Kansas, where we are in the heart of the country, is ideally suited and ideally located to study this question, because this is really the bullseye of where the strongest convection is. So, and the instrument that I work on actually is perhaps one of the central instruments of the mission, because it measures water vapor. And one of the largest signals that we see in our data, one of the largest impacts on the lower stratosphere, is an increase in the water vapor content following thunderstorms. And it was a surprise when we first started to see these signatures in the lower stratosphere, and it took a while to sort of convince ourselves and to convince others that it was actually due to very strong convection. But we were able to show that, yes, we could tie these large water vapor plumes, as we call them, back to very strong convective systems, and then wrote a proposal to sort of study that mechanism in greater detail. So my instrument fits in what's called a spear pod that flies on the right wing of the ER-2 high altitude aircraft. And it measures water vapor, as I said, and it does it in two separate ways. So I have two instruments in this pod that use two radically different techniques to measure water vapor in the stratosphere. And the trick is, you know, ideally they should measure exactly the same thing, because they're both measuring the sample as it's shooting down the duct. The plane's flying, we have an open duct right sticking out of the front of the pod. Air is rushing through that duct, and our two instruments are lined up measuring the water vapor in that system, and they should measure identically the same stuff. And so the reason we have two instruments is because it provides a very rigid constraint on our accuracy. They have to agree. And so if they don't agree, then we know there's something probably wrong with one or the other of the instruments. And right now, the instrument's loaded in the pod. But if I need to do heavy-duty maintenance on it, we can pull it out of the pod, and I can get access to all the parts that I need to get access to. When we're on the ground, we communicate to our instrument with ground support, computer, and power supply. And on the plane, it's completely autonomous. Although what's nice now is that the ER-2 has sort of a capability where we can actually watch the data in real time. It gets sent down from the airplane, well, I guess it's sent to a satellite, and then down to the Earth, and we can see it actually on our computers and watch as we're flying along, and to see whether or not we're hitting the targets that we want to hit. But one of the first signatures that you see when we're looking for these convective plumes is a rapid rise in water vapor. And so when you're sitting up in the, what I keep calling the control room, upstairs where the modelers are and the forecasters, you know, they have their fancy models to show us when we should enter this plume material, but it isn't until we actually see it real time with this instrument that we know we've hit it. And then you can start to see the water vapor go up, and everybody in the room cheers, and, you know. So it's kind of fun.
What is understanding more about water vapor? What does that, in the end, help us understand in the bigger picture?
Well, water vapor is really interesting. It's actually one of the most important greenhouse gases, although it's not one we normally think about, because it's not one that we're actively emitting. It's not an anthropogenic gas, but it's very active in the infrared. So increases in water vapor, particularly in that upper troposphere and lower stratospheric layer, can actually lead to warming at the surface. Water vapor can exist both, well, water can exist both in the vapor phase as a gas, but also in a condensed phase as either liquid or solid particles, ice or little liquid aerosols. And those can also interact with the sun's radiation, either reflecting radiation back to space or also maybe absorbing infrared radiation from the surface. But they also provide surfaces for chemistry. And so there's some chemistry that happens just with molecules in the gas phase interacting, but there's some chemistry that actually needs a surface to happen on. And if water vapor concentrations increase, it can lead to growth in these little aerosol particles. They can get bigger, and that can actually promote some of the chemistry. So it's important for a number of different reasons, actually.